Okay, guys. So far we studied about this first section of the module 5, that is how to define the transducer and different variations of the or varieties of electrical resistance transducer we have studied. In that, the first one we gone through resistive transducer, position transducer, displacement transducers, thermometers, thermistors, LVDT, which is going to measure displacement. And yesterday we gone in detail about the classification of resistance wire strain gauges. A very important discussion we had yesterday, along with the derivation for the gauge factor. So today we will dedicate the session with respect to the instrumentation amplifier using a transducer bridge. So instrumentation amplifier is one part. So this can be clubbed with the bridge or any type of circuitry depending on the specific applications. So let us see how this will looks. So normally the instrumentation amplifier is one of the important, it is considered as one of the important devices as far as instrumentation is concerned. So here you can see we are going to observe this instrumentation amplifier normally in the form of differential operational amplifiers. Here you can see we have got two op amps here, amplifiers having some gain here, adjustable gains with the A1 and A2 names. The top one you can see the input we are applying to the positive terminal, hence it is treated as non-inverting amplifier. A2 you can see here also we are applying input to the positive terminal, it is also another a second non-inverting operation amplifier. And if you look at this one, the negative terminal of both the amplifiers A1 and A2 are connected or fed back to the output. So they are something like acting like voltage followers. Okay. So means the both the op amps A1 and A2 with the non-inverting op amp configuration are connected in voltage follower mode. Then following this discussion, the third op amp where we are applying the output of the corresponding amplifiers, voltage followers A1 and A2 to both respectively positive and negative terminals of the A3. So this final op amp is going to get the difference between these two outputs if it is there. So that will be reflected in the form of a deflection here in the meter having internal resistance Rm. So initially, so another part, let me complete that one. So to these non-inverting amplifiers A1 and A2, so this section is over, this one. This one is your basic instrumentation amplifier. Okay. Now what is another part? Using transducer bridge. Using bridge here, and it is called transducer bridge because you can see the second arm we are using resistive transducer to sense any changes in the resistance. So here you can see the first arm is denoted by RC, that is fixed. The below arm RB, that is also fixed. And these right side arms, the top one is having resistive transducer with a small change in resistance delta R, that is RT plus delta R, followed with below one RA, that is also going to vary. So means initially we can assume that the bridge is balanced, which means that so with this resistive transducer in the second arm, it is known as a transducer bridge. Otherwise, it's simply a bridge itself. So this we are using. This could be anything. This could be a temperature sensitive transducer, or it could be a strain gauge, which is going to measure the pressure or a force like a weighing machine. Okay. So this could be some transducer that will be appearing here as one of the arm of this bridge. That's why it is known as a transducer pitch. This you have to quote, you have to tell why it is called as a transducer pitch like that. So to initially to start with the operation here. So this is all about the construction part what we have discussed. Initially we'll assume that the bridge is balanced. Means that the voltage at A where RB and RC are joining and voltage at point A or node A where your RT and RA are joining. So that both are equal. So in that case we can say that bridge is balanced. Now in that case we can say VA means what? By voltage follower or voltage divider rule. So voltage at point A or node A, this one here. Okay. So you take this loop here, outer loop, like this, as I am showing here. So this outer loop start with the positive terminal of the E DC source to the node and going to RT plus delta R and VA and then RA, then coming to ground and coming back to E. Like this loop I am telling, only this loop. You keep in mind and apply the voltage divider rule. That is to find out the voltage at this node A. That is by Ohm's law, V equal to I into R. So I is nothing but the current flowing through this loop. So that is I is nothing but E divided by total resistance. Okay. So that is going to be here you can see RA divided by E divided by RA plus RT. This one here you can see E divided by RA plus RT. So that is the current flowing through this loop. And as RT and RA are in series, same current will flows. And hence voltage at the node A means voltage across RA, that is into RA you can do. So this into RA if you do, you will get voltage at node A, that is RA into E divided by RA plus RT, that is VA. Similarly, VB if you take, that is voltage at node B, you have to consider this loop here. As I am showing, it is starting with again positive terminal of E, then going to the left side now, RC, VB, that is a node B, RB, ground and coming back to negative terminal of E. So in this loop, the total current which is flowing is nothing but a total voltage divided by total resistance. Total voltage is E, this one, divided by total resistance in this loop is going to be RB and RC are in series. So you just simply add them RB plus RC. So this is the current which is flowing in this loop. And if you multiply this current by RB, we'll get voltage at node B, that is VB. So that's why we have written RB into E divided by RB plus RC. But in balanced condition, as VA equal to VB, okay, so this equal to this, so you can cancel out these two and you will get it as finally RC by RB equal to RT by RA. Okay, so this is the equation or a bridge balance equation we are getting for the instrumentation amplifier using transducer bridge when VA equal to VB. Okay. So next consider another one. So when the bridge is unbalanced, this is the case when VA is not equal to VB. Okay. So here, I hope you can cope up with some discussions are also going on. Am I audible here clearly? Can anyone respond? I can speak loudly. You can hear me. Is it no problem? Okay, let me continue. Let us assume that when the bridge is unbalanced, in that case, VA is not going to be equal to VB. Means that suppose if you take RT plus delta R, and this is second R, suppose initially what has happened in the previous figure when the bridge was balanced? Sorry. So how the bridge was balanced there? So we kept RA, RB, and RC equivalent to RT. No delta R was there. Means all are same. No? In that case, VA is obviously being going to be equal to VB. RA, RB, RC are kept equivalent to RT. No delta R is there. Delta R is coming to picture only when we have unbalanced condition. Here you can see. In that case, you can see guys, as RB and RC are fixed, VB is not going to change much. But this transducer is there no, in this second R. So this one is going to vary. It may be a temperature or it may be a weight or pressure or force or whatever. Accordingly, its resistance is going to increase or decrease by an amount of delta R. Because of that, so R4, sorry, this one, RA is also going to vary. Means voltage across RA is also going to vary. Because the total current is going to vary because of the variation of this. Hence, that current variation in the current is also going to vary the voltage drop across RA. Then we can get VA not going to be equal to VB. Of course, VB may be same, but VA got varied because of the change in the current in this loop which is flowing. That is occurring because of the change in this delta R, what we are now getting. When bridge was balanced, delta R was 0. Now we are getting delta R because of the sensing the temperature or the weight or pressure or force or whatever, depending on the what kind of transducer you are using. So in that case, VA you can see it is going to be equal to the total resistance, total current what we are now getting E divided by RT plus RA plus delta. In the previous was just RA into E divided by RA plus RT. Now RA plus RT plus delta R also now we are getting. Because of this delta R we are getting the variation in VA. But VB you can see it is going to remain same. You can see here. RBE by RP plus RC, RBE by RP, it is going to remain same. So let us see what we are getting. We have to take the difference between VA and VB now. So subject to condition, suppose if you apply this condition RB, RB, RC and RT, we have kept it as equivalent, that is equivalent to R. Okay. So what will happen? So if we make these things conditions here in this equation, so what can RA and RT are equal to R, we will get it as 2R plus delta R as it is. RA will be R and RB again we replace it by R divided by RB plus RC will be 2R. Simplify this one. Finally, you are getting VAB as equivalent to E by 2 into minus delta R by 2R plus delta R. So this much amount of voltage now we are going to apply it to this bridge amplifier, this one, transducer amplifier, consisting of 3 op-amps. First 2 sections are 2 non-inverting amplifiers. Then it will be fed as differential inputs to the differential op-amp E3. So this one we are going to apply because you can see it is in the form of a non-inverting amplifier. You can see the equation, inverting amplifier equation, RF by R1 feedback equation to get the op-amp output voltage. So that is going to be VAB into RF by R1. You can substitute VAB here. So what you are getting, this flow you remember guys. So this is the final output voltage what we are getting for this transducer amplifier using this transducer pitch, instrumentation amplifier using transducer pitch. Change in physical quantity may be temperature or weight or pressure or force reflected in change in resistance, that is a bridge of R plus delta R. So that causes a bridge unbalance. That causes output of the differential op-amp. Differential input will be amplified, that is a differential op-amp output. That connected to the meter calibrated in terms of the units of physical quantity. Okay. So if you are measuring temperature, that will be calibrated in terms of degree centigrade and degree Fahrenheit. And if you are measuring the weighing, then the physical the calibration should be, meter calibration should be in terms of milligram, gram or kg like that. Okay, so this flow you have to remember. So these things you have to explain in your own words. This is very important. So this is the main concept how basically an instrumentation amplifier will work out using transducer pitch. Now let us take how to measure the temperature. Suppose if you are going to replace this resistive transducer arm with the thermistor, Okay, then this setup will be acting like a temperature indicator. Or if you replace this R by relay, then this will be acting like a temperature controller. So remember the difference between the temperature indicator and controller. If you use thermistor here, it will act like temperature indicator, and if you use a relay here, it will be acting like a temperature controller. Remember, this is very important. Most of you make a mistake. What question has been asked in exam and what you are writing. If they are asking you to write temperature controller, and if you do the explanation with a thermistor, no, then whole thing will be wrong. You are supposed to do that one with the relay for the temperature controller. And rest of the explanation you have to do as it is. But in that case, don't do the whole derivation as I explained here. Derivation part not much. If you want, you can do, but do it briefly. With this flow you have to explain. Okay, so hope you are understanding how we can tell this one temperature indicator. Initially you can explain the construction as it is, as shown in the figure. The figure shows instrumentation amplifier using transducer bridge. It is acting like a temperature indicator if the second arm in the bridge is replaced with a thermally sensitive resistor or a thermistor. The remaining arms are fixed, RB and RC. RA is going to vary. And this bridge is energized with the DC supply E. So before the bridge is connected, initially it is connected in the circuit. Next part we can explain. So the second part, as instrumentation amplifier only you have to explain. It consists of 3 op-amps. The first 2 op-amps, A1 and A2, are acting like non-inverting amplifiers. So you can explain how the output of the node A is connected to non-inverting input of the A1, and the output of the node B is connected to the non-inverting input terminal of the A2, and the respective negative input terminals will be fed back. Hence, A1 and A2 are acting like voltage followers. They are non-inverting amp-amps, but connected in the configuration of voltage follower. Then, with the help of another 2 feedback resistors, R1, R2, like this one, they will be applied respectively to the positive and negative terminals of the A3. So here A3 is acting like a differential amplifier, and here output we are getting as a differential output that will be fed to the meter. So initially the bridge is balanced with the VA equal to PB, assuming delta R equal to 0. So in that case, you can explain once again these things, how we have explained with VA equal to PB. So when you will get VA is not equal to PB, same thing you can explain. So whenever there is a change in temperature, that will be reflected in terms of a delta R, maybe plus or minus. So that is going to unbalance your bridge. That is going to affect amount of current flowing in this loop, that is going to affect the variation in the voltage across RA. Hence, we are getting VA is not equal to PB. That is whole explanation we can repeat up to this one in terms of how the meter is going to deflect that one, which is calibrated in terms of degrees centigrade in Fahrenheit, the differential output from the ether. So this is how we have to explain in detail the instrumentation amplifier using thermistors. Same thing, guys. Suppose if you replace this one, all the bridge arms by the strain gauges. Not only this one, remember, very important. All the bridge arms you have to replace it by the strain gauges. So what will happen? These strain gauges are mounted on the base where you are going to put the weight on it. Normal weight scale you have seen, no? Normally it is like a square rectangular structure. On that you are going to put some physical quantity to be measured. Other ಕೆಳಗೆ ಏನಿರ್ತೈತಿ ಸ್ಟ್ರೈನ್ ಗೇಜಸ್ ಇರ್ತಾವೆ. ಈ ಸ್ಟ್ರೈನ್ ಗೇಜಸ್ ನಾಲ್ಕು ಅಲ್ಲಿ ಅಟ್ಯಾಚ್ ಮಾಡಿರ್ತಾರೆ. ಇವು ನಾಲ್ಕರ ಮೇಲೂ ಅದು ಪ್ರೆಷರ್ ಬಿಡ್ತಿರ್ತೈತಿ. Understanding, no? So that is happening there. It is in this form like this: RT1, RT2, RT3, and RT4. So initially, with the weight we are putting, we'll assume that the bridge is balanced. Sorry, the bridge is balanced when no weight is applied. Okay, that is the normal case. Sorry, confused there. As usual, with no weight, the bridge is balanced. And we'll assume that all are equal to R. RT1 equal to RT2 equal to RT3 equal to RT4 equal to R. Hence, the output voltage of the weight scale is 0. So when we will put the weight, we'll assume that RT1 and RT3 will increase because we have seen yesterday that strain gauges one pair will elongate and another pair of wires will one pair of wires are enlarged, another pair of wires are compressed. One pair will be compressed, another pair of wires will be enlarged, elongated. So in the same manner, we'll take RT1 and RT3 strain gauge wires are increased when you put the weight. RT2 and RT4 will assume that compressed or decreased due to compression of strain gauges. We'll assume like that by some amount of delta R. Okay, that delta R will be reflected in this way. RT1, RT3 increased, RT2, RT4 decreased. So this is how we can think of the strain gauges got unbalanced or bridge is unbalanced. So the final VA, what we are getting, VAB plus C into delta R by R. So this differential instrumentation amplifier output then amplifies, giving deflection on the meter moment, which is calibrated in terms of milligram, gram or kc. So the gain you can see V naught equal to V into delta R by R into RF by R1. The meter can be calibrated in terms of grams per kg, grams or kgs. That's all. Okay. So we'll take up one example here to before we'll wind up this one. So many examples are there. I insist you to refer to the study material that I already uploaded in the Google Classroom. The circuit of instrumentation amplifier, the same circuitry. Always we keep this circuitry in mind. This one, this you keep in mind. Whenever you are dealing with temperature measurement or analog wave scale means this and this also you have to keep in mind. So here the circuit of instrumentation amplifier means this one and this one he is referring both. Is converted into analog wave scale using 4 strain gauge elements, each having strain gauge resistance of 50 ohm. Unstrained resistance 50 ohm means balanced resistance. Unstrained resistance means balanced one. Assume that the gain of instrumentation amplifier is 100 gain. E equal to 10 volt. Op amp supply plus or minus 50 nodes. When a certain wave is applied or placed on the platform, the output voltage is 1.5 volt. Okay, means 1.5 volt it is indicating when you put the weight. So determine the change in resistance or the weight is asking. So simply use the formula V naught equal to this one. Substitute the values here. So delta R is the only unknown thing. You will get it as 1.15 ohm. Means when you put the weight, it is showing 1.5 volt. Means it is not indicating 1.5 gram. It may be 1.5 gram or 1.5 kg, whatever. But what this change in resistance it is indicating? It is indicating that your RT1 and R3 are increased by plus 0.15 ohm and RT2, RT4 are got reduced by minus 0.15 ohm. That is the okay. So this is what about the instrumentation amplifier discussion. Very important discussion, very important question. One question is always fixed on this one. So you have to practice, you have to learn the things, understand the concepts and operation very clearly. So one application or both applications should do it along with the numericals. So very important discussion we have today. So here I would like to stop here. If anything else, if you want to ask, you can. We'll continue that one. Let me stop the recording.